go to โรงเรียน
All right. Good morning. Good afternoon, class. Can you hear me okay?
Yep. Good afternoon.
All right. Let's begin with a 1-minute meditation. And by the way, nice to see you again. I mean, nice to be in class with you again. It's been, if I'm not mistaken, it's been 1 whole month since we've had class. So amazingly long time to go between classes. And here we are. All right, so I've got the timer ready. I'm starting it right now. So welcome back to class after a month break. I hope that you had a good Songkran and accidentally a week off last week because I was unexplainably absent. I'm sorry for that. I can't really explain, but thank you for those who sent their wishes of that I would be all right. I'm fine. I'm fine now. Thank you. Okay, so today we are making up a class. So I'm going to teach a double class. It might go an extra hour long, so we might have a 4-hour class today. And we are covering lectures 11 and 12. I have to actually give me a minute. I need to share the links to the slides. I didn't do that yet, so just give me a minute for that now. Okay, I have just posted lecture 11 on Blackboard, so you can go there and grab the slides and to follow along. Before we begin lecture, does anyone have any questions or concerns about anything relating to this class? Someone asked, is our final exam next week? Yes, it is. I know that might be a shock, but to soothe your anxiety, I have decided to make the final exam just like the midterm exam, which means open book, open internet, and collaboration allowed. You can work alone or with someone or others. So this will, yeah, you're very welcome. I knew that would be some good news for you. All right. So more experimentation with this format of examination. I know you like it. I like it too. So we'll keep doing that for this class. Awesome. All right. So now we will go to, does anyone else have any other questions or concerns? Okay, we're gonna go to the lecture now. Lecture 11 is on descriptive statistics. Data must be described before inferring anything from it or from them. Data is a strange word. It's a plural. So, but it's kind of like countable or uncountable, depending on what you're talking about. All right, enough grammar. Descriptive statistics describe quantitative data normally. Well, they can describe qualitative as well. We want to always tell readers the raw numbers of things like the number of participants, conditions, length of study, perhaps, if it's relevant, stuff like that. All right, then there's the mean, median, and mode. These are three important descriptions of your data, your set of data, as a way to describe how the data are spread out or where they exist on the number spectrum. Skewness is another description that can be important. We've got standard deviations. That's a big important one. Percentile rank is sometimes used. Z-scores are sometimes used. You don't have to memorize those formulas, but anytime I present to you a formula in this class, or anytime anyone presents a formula, the reason is for you to get a mathematical sense or grasp. So, all right. You can see here that for mode, your data could be unimodal or bimodal or multimodal. That means that there would be one hump, two humps, or more in the data. Concentrations of scores. Unimodal is probably most common, but well, okay, and skewness, we can have negatively skewed data, which means that if you look at the average, when the data are negatively skewed, the average is on the negative side, or it's on the side to the left of the mode. If the data are symmetrical, the mode is right in the middle. And in positively skewed data, the mean is to the right of the mode. The mean is more positive. So where the mean falls with respect to the mode, that's the direction of the skewness or the skew. Skew is, you could think of it like a skewer. A skewer is that little stick on which you put vegetables and meat to make a kebab, a shish kebab. So skewness and skew come, you could think, remember the skewer is very thin. It's a very thin stick. So the skew is where the data are thin. So negatively skewed means the thin part of the distribution is on the negative end toward zero or toward something negative, or smaller or more negative from the mode. And positive skew is the skewer is on the right side. So that's a little memory device for you. I think you guys know what mean, median, and mode are. Those are important meanings. You have to know what those are. Standard deviation is a measure of variance. Variance means variation, how spread out the data are. The more spread out they are, the more variance, the more standard deviation, the bigger the standard deviation. Okay, yes, you learned it in stats class last term. Good. All right, then. Percentile, if you score at the top percentile, you're at 99 or 100%. Percentile just means where something is if you can divide everything into 100 units. Z-score is a measure of where a score is with respect to the mean. And it is measured in units of standard deviation. So you see that it's divided by SD. So a Z-score of 1 means 1 standard deviation away from the mean. A 1.5 means 1.5 standard deviations away from the mean. All right, next slide. Distribution graph. To make a distribution graph, you should start with a frequency table. That means that on the left of the table, you write down all possible scores or all scores that ever were observed. And then the frequency on the right, you write down how many times that score occurred in your sample. Then from that, you can create a histogram, which is a frequency table or frequency graph. You can see from this histogram that the score of 22 on the self-esteem scale was the most frequent score. And you can see that there's a nice visualization of the distribution of scores. So you can see not only what scores were achieved, but how many of those scores were achieved among your sample participants. So the histogram is a very informative visualization. Next slide, describing relationships. You can describe them with a bar graph. This very nicely illustrates differences between groups. Cohen's D is a statistic that describes differences between groups in standard deviation units. Notice that Cohen's D is very similar to the Z-score on the previous couple slides, 2 or 3 slides back. To measure in standard deviation units is a very handy thing to do because standard deviation is stable for a sample and it varies with the sample variation. So it remains meaningfully tied to how much variety there is in the data. Next, correlations are linear, usually. So we assume that they're linear, but nonlinear correlations can be true also. Here's an example of a line graph and scatter plot. You can see from the scatter plot that it is a linear relationship, more or less. And I say here, it's a good idea to create a scatter plot with your data because the scatter plot shows you visually whether your data are linear or whether a linear relationship is an appropriate description or not. If you don't look at a scatter plot and you just calculate a correlation and you tell your statistics program to automatically insert a straight line to describe the trend, then you're kind of forcing yourself and others to look at your data in a linear way when you don't have to look at it in a linear way. If the data seem to be more U-shaped, then it's not appropriate to describe it in a linear way. So let the data speak to you first before you describe it. And one of the strongest, most powerful ways to let the data speak to you is to create a scatter plot. So that's why I said that it's virtually always a good idea to look at a scatter plot. You don't have to report your scatter plot in your report. You can just look at it for yourself as a first impression and as a way to understand your data before you start describing it anymore.
So for Cohen's D, the larger the D value doesn't mean that there's a bigger difference between M1 and M2.
It does mean that. I mean, D is proportional to the difference between groups.
Okay.
So, for example, you can see that the difference between the purple bar and the red bar is pretty big. So you should see, you could expect a larger D between those groups. Yeah. Next slide, understanding Pearson's R. Pearson's R is the statistic for correlations. There are other R values besides Pearson's, but Pearson's is the most popular one. Numerically, it is the average cross product of z-scores, which are scores written in standard deviation units for all your data points. And how to calculate the cross product of z-scores. In order to calculate your correlation, you do these 5 steps if you're going to do it by hand. No one does it by hand, but they used to. Here's how you do it. Each datum, each data point is transformed to a z-score. To do that, you need the standard deviation and you need the mean. So first you calculate standard deviation and mean, then each data point is transformed into a z-score for both the independent variable and the dependent variable. Every data point, which is called a datum, has a value on the IV and a value on the DV. So each datum is described using 2 numbers, the IV number and the DV number. So you take the IV number, you calculate the z-score, you take the DV number for that data point, and you also calculate a z-score for that. Then you take these 2 z-scores and you multiply them together. That's the cross product. Then then you take all of the cross products for all of your data and you average all of those cross products. Then the result is R. And that R value is the relationship between your IV and your DV. And that relationship would be somewhere between -1 and +1. So -1 is a perfect negative relationship between them, and +1 is a perfect positive relationship. And in practice, we virtually never find -1 or +1. If we found a perfect relationship, then it would not be important to talk about the relationship because the relationship would become an identity. It would be the same thing. Like a perfect relationship between an IV and a DV would mean that the DV and the IV are just different descriptions of the same thing. So we virtually never see the perfect relationship between things when we're looking at correlations. And then how do you describe it when you're writing up your results? You could talk about your mean, your standard deviation, and you would do so in parentheses using an M, capital SD. If there are many means and standard deviations, you could present them all in a table instead of writing them out in the text. Tables are a nice way to present lots of statistics if it becomes too boring to read about in the text. Bar graphs, when your independent variable is categorical, meaning it is not a number but represents categories, then you can represent them as bars. In other words, like if you look at the panel here, in panel A, on the left, you have one category, and on the right, you have another category. I wrote mean one, mean two, just because each bar height is representing the mean of that category or that condition. It is a good idea to include error bars whenever you create a bar graph. And sometimes even when you create a line graph, it's good to include error bars. Error bars represent variation in your data, and that variation exists around a mean. So the bar height represents the mean, and the error bar represents the variation around the mean. How much do the data vary around the mean? The reason that these bars are called error bars, and they're represented here as red lines. The red lines are the error bars. They extend above and below the mean score or the bar height. The reason we call them error is because we acknowledge that when we calculate a mean in a sample, we don't know that that sample mean represents the true mean in the population. So if I measured IQ among 6-year-olds and I had a sample of 36-year-olds, if I get the average IQ of my sample, I don't know that that's the average IQ of 6-year-olds in the whole world. And because I don't know that, I want to include error bars that visually show that the actual true population average of 6-year-old IQ may be a bit higher and maybe a bit lower than the average that I report. The error bar measures how much variance in my data I observed. If I observe a lot of variance, then I can be less sure that the mean is exactly where I said it is in the population. So the less certain I am that the mean is exactly right, the more error there is, the longer the error bars will be above and below the mean. And the error bars are sized appropriately depending on how much variation there is observed in my data. So more variation means more chance that my mean is further from the truth, further from the population mean, or less certain, I should say. It may be spot on, but I don't know that. So there's more uncertainty, there's more uncertainty, so there's bigger error bars. And more uncertainty when there's more variance in my data, more like larger standard deviation, more spread out scores. So the more spread out your scores, the more larger error bars. And you want to include those error bars to present not only where are your means, but how spread out your data were or are. So the error bars can represent standard deviation units or standard errors, which are calculated from standard deviation units, or confidence intervals. All of these things are descriptions of the variance in your data. We will only consider standard error bars in this class because they are common, they're popular, and they reflect not only the standard deviation, but also they are affected by your sample size, your N. We call it N. The letter N for number represents your sample size. So it's a shorthand version to way to say sample size. Because the bar size is affected by the sample size, I'm talking about the error bar size.
So
So
will
if you yeah.
error bars be smaller if there's a bigger sample size?
Yes. If you have a sample of 10, you're going to have very large error bars. If you have a sample of 1 million, you'll have very small error bars. So the error bars provide a visual inspection to see differences between groups. And you can figure that differences between groups are probably statistically significant if the pair of standard error bars, I wrote here overlap. Actually, I mean don't overlap. Let me correct that right now. The difference is unlikely. Hold on, let me read what I wrote. Oh, okay, I wrote it correctly. If a pair of standard error bars overlap, no, that's wrong. No, yes, that's right. Sorry. So if there's overlap, the difference is unlikely to be statistically significant. So you can see here in the panel, on the left, panel A, that's probably statistically significant difference between mean 1 and mean 2. But on the right, we can say that the difference may not be statistically significant because there's some overlap between the error bars. So if we're looking for a statistically significant difference, then we want to see, at least in our mind, just by visually trying to move the error bars in our mind, in our imagination, if we can move them and they don't overlap, then that's a real difference, probably. And if they overlap, then that's probably not statistically significant in that sample. Any questions? Okay. Line graphs and scatter plots. You can make scatter plots when your X and Y axes are continuous, quantitative. So both variables have to be quantitative to make a scatter plot or line graph. If one of them is qualitative, then you're going to be using a bar graph. Trend lines are useful because they visually illustrate the relationship, the angle. If the dotted line is very steep upward, then there's a very strong relationship. If it's more flat, then there's a very weak relationship. And you can also see how strong or weak the relationship is based on how closely the dots are to the dotted trend line. As you can see here on the left, the dots are very close to the dotted line. That means that all of the data hug that trend line very closely. If the data hug the trend, then the relationship is strong. All right, and then on the right here, you can see that even though this is a line graph, there's no trend line. The connecting between conditions here is to suggest it kind of visually suggests a linear relationship. Also notice that error bars were included in this line graph. So error bars can be included in line graphs or in bar graphs. Notice the graph on the left is a continuous data on the x-axis. The x-axis is traditionally the independent variable. And then on the right, you can see that the independent variable is not technically a continuous variable. It's still quantitative because you've got numbers, and the numbers have actual quantitative meaning, but they're not quantities in the same sense as the graph on the left. They are rank quantities, which are quite different. Anyway, so yeah.
Graph on the right, since it looked like the error bars are kind of overlapping, doesn't mean that the data isn't significant.
That's right. It means the differences between pairs of groups that are next to each other is probably not significant. So if you just measured the difference between the first and the second, probably not statistically significant. But you could measure the first and the fourth, and you would almost certainly find they were different statistically. Next, tables. This is just a sample for you to look at, to study and copy in your own report if you are using a table. I did not require that you use a table in this report. Maybe I should require, but nah, I think I won't. I do require you to make a figure though. But someday you're going to make a senior project and you will need to include a table. So here is an example. It has a table, the word table and a number. So table X should be table 1, period. And then the title of your table, notice that the title has capital letters in all of the content words. Notice that it's bold and it's italicized. Then there's a line, horizontal line, to kind of mark the beginning of the table, and there's a line at the bottom to mark the end of the table. Notice that there's on the left-hand column, there's self-esteem column to mark out the conditions. Then along the top, there's negative, positive mood to mark out the conditions of another variable. So you're presenting your data here with two variables, two independent variables. Actually, there are three independent variables here. I'm sorry. On the left, there's self-esteem. That's a dependent variable. And along the top, there's the independent variable. And then there's intention and attitudes, which represents another independent variable. Anyway, so this is a complicated table because you're presenting here data. I mean, this table is presenting data with two independent variables and a dependent variable as means and standard deviations. Anyway, just take a look at it to get an idea of how data can be presented in a table. Here's another table. This one presents a correlation matrix. So we've got table name, title, your independent variables, which are your measures along the... Actually, when we're talking about correlations, they're usually not called independent variables. They're called predictor variables. So they are printed at the top as numbers, and on the left-hand margin, they're printed as numbered names of your predictor variables. So we've got working memory, executive function. Executive function is another predictor. So that's predictor number 2. I see here that okay, I'm just thinking about it. We could think of all of the correlated variables as all predictors. All of them are predictors. Then you could say, well, what are they predicting? They're predicting each other. If something's correlated to something else, then they predict one another. So that's what they predict. So when you're talking about correlated variables, they are often called predictors, not independent variables. Independent variables are when you're talking about categorical variables, experiments, and other kinds of analyses. But for correlation tables, we talk about predictors. So here's a correlation matrix. Along the diagonal, you can see there's blanks. And above the blanks, we see nothing at all, nothing. We don't fill in the blank space above the diagonal because it's redundant. The relationship between variable 1 and 2 is the same as between 2 and 1. And the relationship between 2 and itself is always perfect. It's always 1. So we don't need to print 1. We can just leave it as a blank or as a hyphen or a dash. And we don't have to print redundant information. We prefer not to by tradition. But all of the numbers below the diagonal indicate the relationship between each predictor and each other predictor. So on the column 1, that is the relationship between working memory and the other 5 predictors. They are also called correlates. So it's the relationship between working memory and the other 5 correlates. Correlates. C-O-R-R-E-L-A-T-E-S. A noun representing each predictor variable. Each one is called a correlate. Any questions? Data entry. Once you have collected your data, enter it into a database like Google Sheets or Excel. And then you can format participants as rows and conditions as columns. That's what's done here. Notice this is called table 12.6 sample data file. Never mind the title. Then you've got ID. That can be, every participant gets some random ID number. It could be the number that they participated in, or the number that you received the data back as a stack of papers, for example. So ID, then there's the sex of the participant. So you can see that every row is a participant. The age, the mood, all of these, you could call them predictors, or you could just call them biographical data. Biographical data. Then you've got whatever kind of variables you want. You can find or calculate the standard error of participant 1, or maybe SE stands for self-esteem score of maybe self-esteem from section 1 of the self-esteem scale, and then section 2, section 3, 4, and then a total self-esteem score. And then INT and ATT, those might represent other scales, other measurements. So each column is a category or a condition or a variable, and each row is a participant. That's the way that you should organize your data. Always do it that way, so that if you always do it that way, then everyone else knows how your data are organized. So it's a tradition, and it's nice if we can all be on the same page on that tradition. One more thing, if subscales, let's say that you're measuring self-esteem. You can have a total self-esteem score, and maybe your self-esteem scale has different subscales attached to it. For example, private self-esteem, public self-esteem. It's nice if you have different subscales, it's nice to to enter your data in your database by subscales separately, because that's more meaningful. Of course, you can, add all the subscales together to get a total score, but you don't want to smooth over and eliminate subscale values, because subscale values might be very important to your research. They may be very interesting. You might find an effect with your subscales, but not your overall scores. So the subscale measurements are important to think about, consider, analyze, and keep track of in your database. For today's extended long class, I'd like to give a 5-minute break every almost 30 minutes, I decided. So right now it's 1:48. So come back at 1:53. Let's have a 5-minute break now. Okay? Whoops. I'm back. I gave you 7 or 8 minutes. All right, so let's get started again. Conducting analyses. Step one is to describe your data. Then you can do your inferential analyses. So the descriptive part provides reader with data descriptions. Some examples are Cronbach's alpha to measure the reliability of your survey instrument. You don't need to do that in this class. Central tendency, mean, or median, or mode, but normally mean. And variability, standard deviation, is the most common one for each variable. It is wise to make a histogram just for yourself to see whether the data are unimodal or bimodal, and to note the presence of skew. If you find some unexpected modality and skewness, you should probably report that. Or even if you expect it, you may report these observations if relevant. I don't expect these things to be relevant in your report. I'm just giving you extra information here. Outliers. You can identify them and make sensible decisions to keep or exclude outlier data, and explain in your paper how you treated outliers. For example, you might say that you excluded outliers to avoid undue influence on your mean, or you included outliers because the responses were reasonable and trustworthy even if they were unexpected. So if some data point shocks you and you say to yourself, you have no idea how it's possible that such a data point even exists, and you doubt that it is valid or real, you might report that in your paper, that you had to remove an outlier because it was unreasonable, for example. It's not too common, but just giving you that information anyway. All right, then you'll be doing inferential analyses. The next lecture is on inferential statistics. These are more complex. You can have planned analyses that test your hypotheses. These are the most common types of analyses. You make your hypothesis and then you test it using inferential statistics or inferential analyses. Explanatory are unplanned fishing analyses. These analyses are not to be taken as real in a 100% real sense, but they can be accepted as intriguing, possibly real, possibly deserving follow-up analysis to see if it can be replicated or detected in further research. Exploratory analyses contain much higher likelihoods of type 1 error. A type 1 error is the chance that, I'm sorry, hold on. Type 1 error is when you think that you found a difference, or you think you found something significant because it comes out statistically significant, but it represents a chance finding or a erroneous finding, something that cannot be replicated, something that does not exist in the real world, is called a type 1 error. So when you do exploratory analyses, you have a much higher likelihood of type 1 errors, because when you do exploratory analyses, there's no limit to the number of analyses you can do. So when you find something significant by exploratory analyses, that represents one finding among maybe 10 tests or 20 tests, or I don't know how many tests you might possibly have done. And it's too easy to lie about how many tests were done. So when you limit your analyses to testing only your hypotheses, those are called planned analyses. And when you go off on your own, testing all kinds of other things statistically, those are called fishing analyses or unplanned exploratory analyses. So when you do those unplanned ones, you're likely to find statistically significant findings, but the meaning of those findings has changed because you've done so many of them. So when you do a lot of analyses, the meaning of a significant result changes. It becomes less meaningful, less important. And the reason is because the more analyses you do, the higher the chance that you would find a significant result. And also the more that that result would be a type 1 error. Because type 1 error exists always. But the chance that you would find a type 1 error is increased based on how many analyses you do. So a type 1 error, normally there's a 5% chance that you would find one. That's why, because we set the significance level at 5% or 0.05, that means 5%. If you left it there, you did only one analysis, then you're having a 5% chance of a type 1 error. When you do 10 analyses, you have a 50% chance of detecting a type 1 error somewhere, because you've multiplied the chance of finding one by 10. And if you do 20 analyses, you are almost guaranteed to find a type 1 error. It's not exactly guaranteed that you're going to find one if you do 20 analyses, but the more analyses you do, the higher your chance of finding a type 1 error, or of committing a type 1 error, or detecting a type 1 kind of result, error. Any questions about that? So we control our type 1 error rate by controlling the number of analyses that we run. That means that in order to limit type 1 error, we limit our analyses to the minimum necessary analyses. If you have to do one, do one. If you have to do two, do two, to test your hypotheses. Some papers have 5 hypotheses, so you have to do 5 tests. That means that you have already like 50% chance that one of those analyses is showing you something that's not real. So that's how it works. For discussion, how should we deal with each of the following outliers? You can just shout out your answer. You don't have to raise your hand, just share with the class. In a study of estimation, one participant estimates a woman's height at 2 meters. Should we consider that to be outlier, or, I mean, do we exclude the outlier or do we include in our data?
I mean, since it's a study of estimation, I don't think we have to exclude it.
I agree. That's a good point. Thank you. Let's go to the next one. In a study of memory for ordinary objects, one participant scores 0 out of however many. Should we exclude that data point? Some people are saying exclude. Does anyone want to say include? You might say exclude because you want to test memory among people who have memory. And you might think, well, they couldn't remember anything, so how can I even measure their memory if they can't remember anything? But let me argue against that now, and let's say that we should include that, because when they remember 0 items, that is a measure of their memory. If you're measuring memory and someone doesn't have memory, that is a measure of their memory. It is possible to have 0 memory, and 0 really does mean something. It's meaningful. However, if they're not remembering anything because they got up and left, if they're not participating anymore, and that's why they got 0, now you have a very good argument and reason to exclude. If you know that they had brain trauma, that's another good reason to exclude. If you're trying to measure memory among normal people, then there's a good reason to exclude that. So you have to have really good sound rationale, good theoretical and practical reasons for excluding data. And letter C, in a survey of how many close friends one has, one participant writes 32. What do you think? Include or exclude? Okay. Someone wrote include. I can see arguments for both sides.
Yeah, for me, I think it depends because we aren't really sure what close friends mean. So maybe for this participant, their definition of close friend includes a much wider group of people. Or we said maybe they just really have that many close friends. But I feel like it'll be hard because we don't know what definition close friends means.
Good answer. And someone wrote, maybe the person's an extrovert. Yeah, maybe they're extremely social. Maybe they have, like a really strong social life. So I don't know that we should exclude. If everyone else in the sample has, 3 good friends, 5 good friends, 7 good friends, and then someone has 32, it's very different. It's an outlier, but we don't know that we should exclude it yet. There may be justifiable reasons for them to write 32. So if we don't know otherwise, maybe we should just include for safety. If they wrote 1,000, 1,032, and everyone's writing other numbers that are under 10, then we could you know, being reasonable. We have to be reasonable when we're thinking about our data. We have to use a bit of common sense. And so there, it is a bit tricky sometimes, but I think if someone writes 1,032 friends, then I would exclude. But for 32, I would tend to include. And like someone said already, that it depends on the definition of close. What do you mean by close friend? And then that would impact whether or not you exclude answers. Good. So that's a good brainstorming exercise. Let's go to the next slide. Class exercise. Create a mean, a standard deviation, a bar graph, and standard error. I would like you all to do that now. I'm not going to break you up into groups. I just want you to do it now by yourself. If you could, please open up a spreadsheet, an Excel spreadsheet or a Google sheet. Or if you want to do it by hand, you're welcome to, but that's only for the super mathematicians with calculators handy. Otherwise, open up a platform. Maybe you can copy paste the data. Let's see if I can do that.
The left side is Japan, right?
Yeah. Japan's on the left, US on the right. These are made up data.
Could you go back to that? I didn't
Yeah,
see.
sure. I'm gonna really quickly open up a spreadsheet. In Google Sheets just to paste the data. You can copy the data from here if you like. Slow. I don't know if you can see the data on my screen.
Yes, we can.
Okay. Okay, so we need to calculate the mean and the standard deviation. And this is a kind of, you could call it our lab activity to learn how to do that. So I'm going to show you how to do it now. And then I want you to do it by yourself on your own computer. Copy the data for, let's say, which one is this? The Japanese data, right? So highlight all that data. Oh, wait, no. No. Okay. At the bottom, type equals average. Type the word average. So equals average, open parenthesis, and then use your mouse and click and highlight all of the cells. Let go, close parenthesis, enter. So the average is 25. I'm going to do it again. Equals average, open parenthesis, highlight, close parenthesis, enter. 31. We have now calculated the mean. While you're working on that, someone asked about planned and exploratory analyses. Planned analyses test your hypothesis or hypotheses, which you stated in your introduction section of your paper. You're supposed to type, you're supposed to tell your readers what your hypotheses are, what you expect to find, and then that becomes your planned analysis. Exploratory analyses are anything that you're curious about and interested in that you did not already you didn't report as your primary hypothesis. Okay, so now we have the mean. Did everyone get the mean? Are you still working on it? I'm not surprised if you're still time to type out all of these numbers and you might not be able to see clearly on my screen. Let me see if I can zoom. I can't. Oh, there I can. Okay. All right, what I did was I typed out all of the numbers. I will add the data labels. And then we calculated the mean using the formulas that are used by Excel and by Google Sheets. If you can't do this, just follow along. Maybe take notes if you like. All right, now let's calculate the standard deviation. To do that, wherever you want the value calculated, type equals STDEV. STDEV calculates the standard deviation. So there it is. And then open parenthesis, Careful not to copy your mean. So you're going to highlight your data. And then you can just press enter. You don't have to close parenthesis. If you just press enter before closing it, the program does it for you. All right, so our standard deviation is 4.11. Now let's do it again. Equals stdev, open parenthesis, copy the data, enter. 4.59. We usually round our statistics to 2 decimal places.
STDEF, right?
No, V as in victory.
What is it again? Sorry. STDEV.
Yes,
Okay, thank you.
sure. All right. Do you need more time? Anyone? The next exercise is to make a bar graph. All right, that's a big one, challenging one. This is important for your paper. You have to put a figure in your paper. Your figure is most likely either a bar graph, a line graph, well, basically one of those two, probably. All right, so let's do that. To do that, we might need to use the means and the standard deviations. All right, let's start with the mean. All right, so to make my bar graph, first thing is I'm going to highlight the means that I want to use. Actually, no, let me change this. So we've got 25 and 31. All right, so let's go up here and start again. So Japanese, American, 25, 31, and label this self-esteem. Now I'm going to highlight not just the numbers, but also the labels, Japanese and American. Once I have highlighted those, I can go up to insert. No, yes. Insert image. Let's see what happens. Okay.
There's a chart there. Chart like Bart.
Where do you see chart?
Or right above image. Right above image. Right there.
Oh, yeah. That's even better. Chart. Thank you. That was it. Okay, I selected it and nothing happened. I'm going to try. Oh, there. Okay. I'm going to zoom out. All right. I used to be more detailed about how to format everything. I think I'll skip out on some of the details due to time, and I don't want to overwhelm everyone. You don't have to do this, but if you can move your mouse right over the grid lines, and then click on the grid line, any one of the grid lines, and then press delete. It says it cannot be deleted. Okay, never mind. I think I'm not going to spend more time formatting this. Really, we should add axis titles to the y-axis and to the x-axis. Maybe, let me see if I can figure this out really quickly. If I can't, I'm just going to move on. Whoops. If anyone knows how to add axis titles, you can speak up. I'm not used to doing this in Google Sheets. Okay, right click in the chart area and go to chart and axis titles and scroll down, find horizontal axis title, select. And then in the right hand margin, you see the chart editor, which you can type in the title. Let's type nationality for the x-axis, your categorical, your independent variable. And then maybe scroll down to where it says vertical axis. Select that. Oh, no, not that. Sorry. Chart axis and titles again. Huh. Oh, I see. Then there's a little drop-down menu where it says horizontal axis title. You can click that and select vertical axis title and type in the title text of self-esteem or self-esteem score, whatever. All right, now we have done that.
Do we need an overall title for like such graphs?
An overall what?
Do we need an overall like title, heading?
No, because to correctly format your figure, you should put your figure title in the text, not in the figure. Thank you for asking. What I mean by that, okay, let me show you what I mean. So once you have your figure, click on it, copy it. Can I copy it? Okay, I'm just gonna use Control C to shorthand key, copy it. Then I'm gonna go to a document. And paste it. It's not giving me the, oh, here. So I'm going to show you what I mean, how to create your figure. First thing is centered, the word figures. This is at the end of your report. Then I'm going to paste the figure. Then underneath the figure, I'm going to type figure 1, period, self-esteem scores by nationality, or something like that, period. And the rule is to be as informative as you can. So let's type mean self-esteem scores on the Rosenberg self-esteem scale by nationality. Something like that, to give a lot of detail about what is in your graph, because you're not going to provide any other detail besides the title, if possible. If you did have to put more details, you could have a footnote or no, not a footnote. You could describe more here, more description if necessary. Okay, so that's how you make your figure. Now, one more task for us here is to create error bars, which I want you to do in your paper, in your figure. Okay, so SE stands for standard error bars. All right, this is maybe going a little bit complex. So I'm adding another kind of statistic we're calculating here. It's called standard error. All right. The standard error is calculated as the standard deviation, B13, divided by the square root of, so I'm going to type SQRT and then open parenthesis, the number of data points that you have. And there's 10 data points. So type in 10, close parenthesis, 2 times, enter. Sorry, this is all very complicated, I now realize. I guess I'm sorry it's so complicated now. I'm getting a bit advanced on you suddenly. So I'm gonna type out what I did. SD divided by SQRT N. So let's do that again for this other sample here. Someone asks, is this going to be on the exam? It could be, but you know how to look it up. All you have to do is type into Google standard error, and you'll find this out. So let's calculate this again. Equals, now I'm doing this for the USA data. So go into your cell, type equals, and you can start by clicking on the standard deviation just in the cell above, and then press slash, which means divided by, and then type SQRT for square root, and open parenthesis 10, because there are 10 data points. That means there are 10 participants. And enter. So now we have our standard error units. We're going to use these standard error units to create our standard error bars, which we're going to insert into our graph right here. Okay? If possible. I haven't used Google Sheets to do this before, so this is new.
Sorry again. For the SQRT, what we put in there again, the mean, right?
No, N. N is the sample size. Sorry, don't type the letter N. Type 10. That represents the sample, your sample size here. All right. Let's see if I even can figure out how to add error bars. And I guess this is different if you're working in Excel. I don't think I can figure it out yet. Okay, let's just skip that. Wish I could do it. Yeah, I guess I can't figure it out right now. If I find out how to do this later, I can email you about it. But if I don't, then I cannot require on your figure something that I cannot teach. So if I figure it out, I'll let you know. If not, then you don't have to do it. All right.
Okay.
Okay. Did I explain how to make a figure well enough? Were you able to make a figure?
Yeah. If you do it on like the Google X, I mean the Excel, you can easily like add stuff like the error bars. It's a part of the system to add more.
Yeah, it's easier in Excel. I was trying to do it in Google Sheets in case people cannot access Excel.
Yeah, I had to. It took me a second to catch up because I was using Google Sheets at first, and I had to transfer everything over to make it easier.
Good job. All right, I think we've done enough figure making for now, and I think we can go back to lecture. Do you guys want a 5-minute break now?
Please, please. Thank you.
Yes, let's do it. Okay. Take a 5-minute break. We'll start back at 2:46. Welcome back from the break. Let's go on. Next, we have another exercise to create Pearson's R, a scatter plot, and a trend line. And we're working with another set of data, extroversion and Facebook friends. So extroversion score represents a score on some hypothetical scale or measurement device, some scale. Facebook friends there. All right, so let's take a moment to copy this over and type it out. So I have to do this too, so I'm gonna stop sharing. Sharing my screen, you can kind of follow along if you like, or you can be doing this also. So we're working with a smaller data set. Okay. So the assignment is to find Pearson's R. That's the first thing. To do that, I'm just going to go over here. Type Pearson's R. Let's see. To do it, type in equals correl. Correl stands for correlation, and there it is labeled here, Pearson's product moment correlation coefficient. So you get that using equals correl for correlation. Open parenthesis, and then you can click and drag to highlight all of the data all at once. And then you can close parenthesis or just press enter. And there it is. Wait, what's going on? The problem is, I don't know. I'm going to try that again. Wrong number of arguments. Oh, okay, I know. Sorry. I told you wrong. Here's how you do it. Equals correl. And just one column of data, comma, another column of data. So you have to do it in 2 highlights or 2 steps. Highlight one column of data, comma, type comma, and then the other column of data, highlight that, and then you can press enter. So I calculated a correlation coefficient of 0.38. Did you do that? Can you do that? Any trouble?
No.
Yeah, it went well.
Sorry, what? Did it work?
Yep.
Excellent. All right, so we've done Pearson's R. The next is scatter plot. Let's try that. I'm going to highlight all of the data and see if I can insert a scatter plot. So it gave me a bar chart first. I'm gonna see if I can select something else. Right next here is a scatter plot. So I'm gonna choose that from the drop-down menu, and here we go. I got a scatter plot. So I went to insert, I selected chart, and then I selected the scatter plot from the suggested chart type, whatever, under the setup options. So I could have used a bar graph or many other kinds of graphs. As you can see, there's many options, but the second one just to the right was scatter plot. All right, were you able to do that? Anyone have any trouble? Not that I can certainly help you. I don't know if I can help you from here, but I hope that was clear. And the last thing on this slide is to add a trend line. So let's do that. Or maybe I can't. I'm going to customize grid lines and ticks. Let's see if I find it. No, not there. I think this is another case of I can't figure out how to insert a trend line. In Excel, it's really easy. There's a choice to just insert it. So maybe the moral of the story is to use Excel instead of Google Sheets. I'm sure Google Sheets can do it. I just don't know how. Yeah. I don't know how to do it. So if I find out, I'll tell you. Otherwise, I will not require a trend line if you in your figure, if you're making a scatter plot, because I didn't teach it. So I guess that's it for that exercise. I hope you were able to create a scatter plot and calculate Pearson's R. Those are the two more important things. Okay, so I will go on now. To another practice assignment. This one says, make a frequency table and histogram for the following data. Use your hand or a computer. I recommend computer. Describe the data, the shape of the data, the modality, and the skewness. Compute the mean, median, mode, standard deviation, and range. So you can do this at the same time that I work on it. Let's all work on it together. So your first step would be to take all this data and move it into, or type it into a spreadsheet. Or maybe you don't have to. We're going to make a frequency table in order to make a histogram. So on the left, we have the value, and on the right, we have the frequency. I'll just type that to help you out here. Labels. All right, so we've got an 8, 9. Oh, we've got a 6. As you can see, we've got one each of those. count 2 10s. So next to my 10, I put the frequency of 2. Then we've got 3 11s, 4 12s, if I count correctly, 2 13s, 2 14s, 1 17. All right, now I've got my frequency table completed. You might take a little longer, or you might have finished it already. Step 2, highlight the data. Insert a chart. As your chart type, change it to the third option, or second. It's called histogram of frequency. So select that. All right, we have done it wrong. Somehow it's not right. We need to flip the variables somehow. Okay, I figured it out. Where it says x-axis, you can click on it and choose not A43 to A51, but B43 to 51. And the next one, change that to the A. All right, I think that fixed it more or less. I don't know, it still looks weird. Looks wrong. 6 should be 1, not 2. I think it's grouping the data somehow, and I don't want it to group the data the way that it's doing that.
Is Excel much easier? Wait, not. Yeah, is Excel much easier to use?
In my opinion, yes. But for someone who's not created a histogram in Excel before, I don't know if it's really easier or not. I know that I'm having trouble with Google Sheets. Maybe Excel is easier. I hope it is, because I'm having trouble. Does it work out better for you?
For me, I'm having the same problem on Google Sheets.
Uh-huh. Do you have Excel?
Not on this laptop.
Yeah. Guess I should have tested this first. Somehow the program is aggregating my data more than I want it to. it should be showing like values of 6 and 8 and 9, but it's not doing that. Oh, I think I got an idea. All right. Let me do the, I think I figured it out. Okay. I'll show you what I mean. So I should have put a 7 in here. I should not skip any numbers. If there are 0 instances of 7, I should still put the value of 7 and then a 0 next to it. So let's see if that fixed the problem. I'll try again. Yep, that fixed it. That was the problem. I skipped. I was a little bit too fast and sloppy. And so you have to make sure that when you're making a frequency table, you have consecutive number like 6, 7, 8, 9, 10, 11, 12, 13, 14. Even the 17 I messed up, or it should be 15, 16, 17. All right, now this is a properly created frequency table or histogram. So you can see the blanks for 7 and 15 and 16. That's necessary to help Google Sheets generate the chart correctly. And it's a good practice. I should have done that. Otherwise, the viewer or the reader might accidentally assume that there was no, that every single number was represented, and that's not true. There's some numbers that are not represented in the sample. So we do need to insert all like a consecutive series, an uninterrupted series of numbers along the x-axis. Then it will generate correctly. Were you able to do that?
Yes.
Great. I hope so, because if you're not, I don't know how to help. The next task is to describe the shape of the distribution. Let's describe the shape of our histogram in terms of modality and skewness. All right, let's look at the modality first. How many modes do you see?
1.
1. Someone could say, I see evidence of another mode here at number 14, but I don't think that there's a strong argument for calling that another mode. I think we only have one mode here. Technically, there's only one mode, and even visually, we can see that this grouping of data suggests basically one mode. A grouping that would suggest 2 modes would be like if the bars were higher at the lower end, lower in the middle, and then higher at the upper end. If that, then we could say it looks bimodal, but right now it looks unimodal. And now the next question, is there any skewness? What's the skewness? How's the skewness looking?
For
Do
me,
you see?
Kind of looks normally distributed.
Kind of, yeah. If anything, if there were any skew, would it be a positive skew or negative skew? Oh, well, actually, that's a interesting question. If anything, I mean, maybe it's slightly
Negative.
slightly negative. Yeah, just very slightly. But mostly no skew. Yeah. Yeah, I think that's correct. Okay, next question. Compute the mean, median, mode, standard deviation, and range. Okay, let's do that. Median, mode, the range. Okay, I'll show you how I would do this. There's two ways. You could type out all of the numbers, which is what we started with. So all of these numbers, you could add them all together to make a mean. I'm going to do it like a little different way. I'm going to multiply the value and the frequency together. So equals A43 times B43. Now that's a product. So if there's only one of them, it's 6. If there's two of them, it would be 12, etc. Now I'm going to copy and paste that formula to all the other cells by clicking on the calculated cell. So this cell that says 6 in it is representing a multiplication of two other cells. And in the bottom corner of that cell, there's a tiny little square. I'm going to click on that square, click and hold, and drag it all the way down as far as I can go. It's supposed to drag it all the way to the bottom. All right, there. Now I've got all of the values represented in the right number. So for example, 14, for the number 14, the total is 42 because 42 represents 3 14s. All right, so then I'm gonna use that to calculate my mean by typing in equals average and then select all of the data, all the represented data. So the average is 17.42. Next, how about the median? I'm going to type equals median. And I'm going to highlight all the data again. Again, you could do this using the actual data. You could type in, like, instead of 42, you could have typed 14, 14, 14. It doesn't matter how you do it as long as you know what you're doing. So 14, 14, 14 represents 3 14s that we found in the data, for example. So using this data set, you could find the median, or you can use the data set that I created here by multiplying the values and their frequencies. Either way, it works. All right. The third one is the mode, equals mode. And If I do that, I'm going to get the wrong value because the mode is going to, the mode looks for the most common number. So I'm just going to do that one by hand by looking at my data from the frequency table. And I can see that the most frequent value is 12 because there are 4 of those. So my mode is 12. Does everyone understand that? Or do you have any question about that? About the mode? Or the median or the mean? Anyone? Okay, the next is standard deviation. So I'm going to type equals STDEV, open parenthesis, highlight all the data, enter. Now I've got my standard deviation. Oh, but it's not correct. That's wrong. Tricky. I think to calculate the standard deviation, I would need to type out all of the data individually. Like if there are 3 14s, I have to type them out 3 times, 14 3 times. Then if I had typed out all of my data, I could highlight all my data and then I could use that to calculate my standard deviation. In the interest of time, I will skip it because you already know how to calculate standard deviation. Finally, for range, I can just type equals range, I think. Let's see. And for this one, I'm going to go to the values because range doesn't matter how many of them there are. It just means what's the minimum, what's the maximum. And that didn't work. Another way to do it is equals the largest value of 17 minus the smallest value of 6. So largest minus smallest, 11. The range is 11. Any questions? We have completed that practice assignment. That concludes lecture 11. Do you want a break before we go on to lecture 12?
Yes, please.
Terrific. We'll start at 3:24. Have a 5-minute break. See you in a bit. Okay, it's 3:24. Welcome back. We are going straight on to the next lecture. Lecture 12 on inferential statistics and how to analyze your data. I hope that everyone has collected your data already. And if you have, good job. Pretty neat that everyone can create a research project, collect data, and analyze it all in one semester for just one of your classes. Pretty cool. Inferential statistics. Once you have a result, the next question is, does this finding generalize to the population? To answer that question, we do inferential analyses. And most inferential analyses are done to test a hypothesis against another hypothesis called the null hypothesis. Null means nothing. It means zero. It means it's like the absence of a hypothesis. But it is a hypothesis. It's the hypothesis that there is no effect or no relationship or nothing interesting to talk about. So basically no effect or no relationship. We test our alternative hypothesis against a null hypothesis. This is the traditional way to think that your results generalize to the population. In a sample, we calculate statistics which describe a sample. In a population, we estimate parameters which describe the population. Notice the lineup of those two sentences, how they are lined up in parallel. That's so that you know that the equivalent of sample at the population level is called population. At the sample level, we calculate. At the population, we estimate. At the sample level, we talk about statistics. At the population level, we talk about parameters. Parameters are just the word we use when we're talking about a population. Yeah. Any questions? All right. When we obtain statistics from our sample, either the sample matches the population exactly, which is rare or impossible, or the sample statistics don't match the population due to sampling error. We virtually always have sampling error. That means that the sample does not represent the population. The sample virtually never represents the population. All we can hope for is that it approximates the population, that it represents the population in a more or less fair way, but it never, virtually never matches the population. So if the sample mean is 12, that doesn't mean the population mean is 12. There is some unavoidable error when we use a sample to estimate a population. But we don't know the population, and we probably can never know the population because we probably never collect all data from all members of a population unless it's a small population. Hence, we commit type 1 errors and type 2 errors. We try to limit frequency of committing errors. Null hypothesis testing continued. Imagine you find a small difference between conditions. In the null hypothesis, the null hypothesis is represented with H sub 0.
Excuse me ค่ะ I think you haven't pasted the slide on Blackboard ค่ะ
Oh, thank you. Yes, you're right. I'm going to do that right now. Okay, they are there now.
Thank you ค่ะ
Thank you. Okay, am I still presenting my slides? Can you see this slide?
Yes, we can.
Great. H sub 0, or H lower script 0, is to represent the null hypothesis, which is the difference between conditions is due to sampling error, chance. In other words, there is no effect. There is no difference between conditions, or no real difference. That the effect is 0 in the population. Or if we're dealing with correlation research, then the null hypothesis is there is no relationship between the variables. And any apparent relationship is just due to sampling error or chance, accident. So that's the null hypothesis. And we test that against the alternative hypothesis, which is often written as H sub 1, lower script 1, or H lower script A for alternative, H sub A. The difference between conditions reflects a real effect that exists in the population. That's the alternative hypothesis. If you want to support H1, then you want to reject H0. That's how you support H1. So in hypothesis testing, null hypothesis testing, we support our hypothesis by rejecting the null hypothesis. Technically, all we can ever do is reject. We can never accept. We can only reject. That's the only thing we can do when we're using this form of statistical analysis. Basically, most inferential statistics work by rejecting the null hypothesis. To decide between H sub 0 and H sub 1, we measure the effect size using sample size and variability. And we calculate the chance of finding an error in this size if there were no effect in the population. So we assume, this is a little confusing because normally you think you want to support your alternative hypothesis, but for the sake of hypothesis testing, we have to assume just temporarily that there is no effect in the population so that we can test the null hypothesis and see if we can reject the null hypothesis based on our data and our observations. We reject the null hypothesis if it would be unlikely to find an effect of this size in your sample, assuming no effect exists in the population. We more or likely accept the null hypothesis when the effect that we observe in our sample is a small effect. And also when the when the sample size is small, we are likely to accept the null hypothesis because small sample sizes make it hard to reject the null hypothesis. Any questions? This is complicated. conceptually, this is complicated. Researchers want to support their alternative hypothesis, but they do so indirectly because all we can ever do is reject the null hypothesis when we are using null hypothesis testing, which is like 95% of the time when we're doing research in psychology, we're using null hypothesis testing. So the best we can do is reject the null hypothesis. Next slide, the p-value. This is called the probability value. And that's what P stands for. The most misunderstood statistic in psychology is the p-value, I would argue. I think the textbook agrees. P is the probability of obtaining the sample result while assuming the null hypothesis is true. So just like I said on the previous slide, we have to assume the null hypothesis is true while we are conducting null hypothesis testing. And it is by rejecting that null hypothesis that we indirectly support our alternative hypothesis. So we use the p-value to indicate to us whether we should accept or reject the null hypothesis. The p-value is the traditional statistic to make decisions between H0 and H1, the null and the alternative. If the p-value is greater than 0.05 by tradition, we fail to reject the null hypothesis, which means that we do not accept the alternative hypothesis. 0.05 exactly means there's a 5% chance that the null hypothesis is true. If we get p equals 0.06, we mean there's a 6% chance that the null hypothesis is true. And if there's a 6% chance that the null is true, then we conclude, we say we cannot reject the null hypothesis. But if the p-value is 0.049, then we say we reject the null hypothesis because there was less than 5% chance that the null hypothesis was true. So if there's less than 5% chance of it being true, we reject it. That's rejection of the null hypothesis. So when the p-value is less than 0.05 by tradition, we found what we were looking for. Does that make sense? We find what we're looking for by rejecting the null hypothesis, by saying that it is too unlikely to be true. So our attention, with the p-value, our attention is on the null hypothesis. But hardly any researchers are really thinking about the null hypothesis when they're testing it, because they're so excited to find out whether their alternative hypothesis is right. But you now, if you're understanding me and if you're listening, when you look at the p-value, you should not be thinking about the alternative. You should be thinking about the null hypothesis. because that's what the p-value is. It's about the null hypothesis. Does that make sense?
Yep.
Great. When the p-value is less than our criterion p-value, which is called alpha, symbolized with that fancy A symbol, that's where we get the letter A. It's, alphabet. That little alpha symbol is used as a symbol for our criterion p-value. That's the p-value that we make our decisions based on. And that's, by tradition, 0.05. So alpha is usually 0.05. P-value is whatever we find. And we find and compare what we find in the p-value, we compare that to alpha, which is also called p equals 0.05. We call the result significant if it's less than alpha, if the p-value is less than alpha. That's called significant. Significant in a statistical sense does not mean significant in a real everyday sense, because in the everyday language we use when we talk about something as significant, it means that it's important. But when we talk about significant in a statistical sense, it doesn't mean important. It means below p equals 0.05. So it's not the same as important, meaning the result is important, because sometimes less than 0.05 is still not very important. It depends on what you're talking about. It depends on the variables. It depends on what analysis you did, if you did it properly. So we're not judging importance here. We're judging the null hypothesis, I guess. So this is an unfortunate, confusing word to use in our field of psychology to describe statistical results. I wish that our field described p less than 0.05 as statistically likely instead of calling it statistically significant, because the p-value, p stands for probability. So it should have been just left as the word likely or probable or something like that. It is the likelihood that the hypothesis, the null hypothesis, is incorrect. And I wrote some notes at the bottom of the slide on this slide, so I'm just going to read those out loud to you. I wrote this a couple days ago. Due to the confusing description of p less than 0.05 as significant, our field has continued to dwell on and make a big deal about findings no matter how big or small their effect sizes are. Because when a finding is found to be significant and labeled as significant, it is also by virtue of confusing the word choice with the meaning of significant in an everyday sense, it's often taken to mean that it is important, when statistically significant findings are really not important sometimes. Effect sizes are super critical to judging the importance or the worth of a finding. You could find a significant value that's very, very small, which means it's not very important. With large enough sample sizes, any small, unimportant difference between groups can be described as significant, even if it's very, very small, just because the statistics reveal a real difference. No matter how minor or unimportant that difference is. For example, the difference between happiness between those who wear a shirt with a pocket and those who wear a shirt without a pocket might be expected to be unimportant and minor, but with a sample size of 1 million participants, the results could be detected that one shirt type is ever so slightly leading to slightly more happiness than the other shirt type, and that might be technically true, but is it important? Does it matter that the shirt pocket elevates happiness by 0.00001%? Will that affect your dressing? Will it affect your purchasing decisions? Probably not. It should not matter because it's such a small effect size. Because such a small effect size would not even be conscious, would not be expected to be meaningfully influencing much of anything at all. Remember, statistically significant does not mean significant in the sense of being important or meaningful. So that is my sermon to you about the word significance in a statistical way. Sample size, effect size, and significance. Small n, sometimes written as capital N, sometimes lowercase n. I guess it doesn't matter. So small n, if you have a small sample or a small effect size, which is written with the letter D, also called Cohen's D. I don't know why D, but D means effect size. We can expect it's probably insignificant. So if you have a small sample and you're trying to measure a small effect and you find that small effect, the effect is small, we expect that your test of the difference between groups or conditions or the size of the effect, we expect the statistic will come back that P is greater than 0.05, which we call insignificant. But if you have a large sample, you're testing a large sample to detect a small effect size, then we are likely to find a significant result because large sample sizes are very sensitive to finding and detecting significance in the p-value. If you have a small sample but a large effect, then you may find a significant finding. Probably, let's say probably. And with a large sample and a large effect, I don't even have to say probably, I can say almost certainly you will find significant effect, meaning that P is less than 0.05. In the case of R, which is the letter representing correlation, R means correlation. If your correlation size, so you're going to measure your correlation size instead of your effect size, it holds the same pattern. Same pattern holds. So we'll talk about that a little more in a slide or two. First, let me talk about trivial versus small but important. The word trivial means unimportant. So if an effect is small, it can be significant, but it can still be called trivial. Trivial means unimportant. So the difference between gum and sugar-free gum on weight gain can be called trivial. Yes, it has some effect, but it's such a small effect and so unimportant that we call it a trivial effect. So there's your vocabulary for the day, if you didn't already know that word. Next, smoking a cigarette every day may have a very small effect on longevity, yet we do not call it trivial because human life is concerned. So it depends on what your variable is, whether you call the effect trivial or not. If it's life and death, we don't usually call it trivial, even if the effect is very small. So the effect of a cigarette on your health is very, very small if it's just one cigarette. But the effect of one cigarette a day, even if one per day for many years, is still a small effect. We don't call it trivial because we're talking about death, which is very meaningful. The relationship between sun exposure and skin cancer is probably not trivial because, again, death is concerned. However, that doesn't mean that you should avoid sunlight, even if the effect is very, very small. Or sorry, if that small effect is there and it's a life or death effect, don't avoid sunlight because it's risking death. You have to take account of the effect size. And also you have to consider the alternative of avoiding sunlight. That's even worse than getting it. So we need to be aware of effect sizes and how important those effect sizes are. Small doesn't mean unimportant, but sometimes it does mean unimportant. So you just have to kind of judge from context, from the variables and the implications. You have to judge whether the effect is meaningful, not just based on whether it's a big effect or a small effect, but what the implications are, what's concerned. Next slide, the t-test. T, there's the formula for it. T, the t-value is equal to the group mean, subtract the null hypothesis mean, I think, or subtract another group mean. So you're getting a difference between groups or a difference between your group and a hypothetical mean. All right. And then on the bottom of the fraction is the standard deviation. So you're measuring in standard deviation units, but that standard deviation is then further qualified or shrunken by the square root of the sample size. Basically, on the underneath side of the fraction is the standard error, because that is the formula for the standard error. Anyway, so T is the group differences divided by standard error. And then you don't know whether that's a significant effect or a t-value or not, because we need the p-value associated with that t-value. I'm going to read from the slide here. The t-test is a measure of difference between two groups or a group and a hypothetical value to indicate the likelihood of significant difference. The critical t-value associated with your alpha, let's say p equals 0.05 is your alpha, will vary depending on your sample size. To reach alpha, the critical t must be larger if your sample size is small, but your t-value can be not so large if your sample size is large. So for large sample sizes, you don't have to achieve a very large t. You can achieve just a like t of 1.5 or 2, or it depends on how large your sample size is. The larger your sample size, the less large your t has to be to achieve a significant difference. Someone asked, how is the t different from Cohen's d? That's a great question. And the answer is, in the case of d, Cohen's d, the bottom of the fraction is SD, the standard deviation. But in the case of t, it's the standard deviation further divided by the sample size square root. So the d value, Cohen's d is going to be smaller and t is going to be larger. But they are very conceptually close. They're very conceptually close. If you have a large t, you're going to have a large d, and vice versa. Those two things are very strongly correlated together. They're very similar conceptually and statistically. It is called critical t because if your observed t is smaller than critical t, you did not find an effect. So your t has to be bigger than the critical t. And you get the critical t from a database or a published table. Back in the old day, before we used computers a lot, there were published tables of t values. So you would calculate your own t, and then you'd look up in the in a t value appendix to scroll down to where you find your t value, match it up with the sample size, and then you would see whether your t value was significant or not. That was back in the old day. Now we just, computers are so quick and easy and powerful, we don't have to compare our t values to physical tables anymore. It's crazy because when I was in graduate school, they were still teaching us to look it up in tables, even though our statistical programs were already doing it for us. The instructors thought it was good practice. So I guess that's why I'm still talking about that stuff. But really, we never use printed t values anymore. We just press enter in a statistical program and voila. So, but it's good for you to understand it at a conceptual level. Really, it's really important. Your t value is compared to a critical level t value to ascertain or decide whether your effect is significant or not. It's all mathematical, it's all done for you, but this is how it works. The large sample size is associated with small critical t. Larger sample size is associated with smaller, critical t. So it's easier for you to get your t value to be higher than that critical t because the critical t is smaller for larger samples. So the critical t is adjusted based on how many participants you test. What your sample size is affects or specifies your critical t. Hence, large N studies have greater statistical power to detect an effect. All right, I think I'm using kind of overly complicated language to describe a fairly simple concept. Basically, it's like this. A large sample size means you can find a significant effect even when the true difference between groups is not too big. So powerful, large samples are statistically powerful at detecting significant effects. Statistically. This figure illustrates the critical t value that your own sample t value, that when you calculate the t value for your study, if your t value is larger than the critical t value, then you found a significant effect. So if you're doing a one-tailed test, the critical t value is closer to the null, closer to 0. If you're doing a two-tailed test, then the critical t is further from 0. In other words, larger. Now, the indicated lines by green and red here are just for some hypothetical sample size. If the sample size is larger, these green and red critical t level lines would be closer to 0 for larger sample sizes. But for smaller sample sizes, the critical level moves further away from 0, either in the positive or negative direction. If you're doing a one-tailed test, you would have the critical t in only one side. It's illustrated on both sides here because we don't know if the test is testing in the positive or negative direction. But for two-tailed tests, the critical t exists on the negative and positive ends, because you can have a negative t or a positive t, and it really doesn't matter if your t is negative or positive. It just depends on the particular groups, the particular data. For t values, you can ignore whether it's positive or negative. It doesn't matter. Next slide, the t distribution. And its shape indicate the probabilities of obtaining t values when there is no effect. The difference between groups. So if there's no difference between groups, the t distribution should be centered at 0. That's why this t distribution is centered at 0. This is called a t distribution. Anyway, so the probability of getting a 0, like t equals 0, is high if the null hypothesis is true. That's why the t distribution is centered around 0. The t distribution changes shape from short fat to tall narrow as the sample size increases. I think I got that right. This is getting really abstract anyway, so it's okay if you don't understand. Or even if I said it wrong in this language, it's really quite high level, abstract, and you don't so need to know or understand this. It's going kind of high level. Anyway, next. With a given sample size, say n equals 25 for the t distribution illustrated. Yes. So I am right. The distribution can be short and fat for smaller sample sizes, or tall and short for larger sample sizes. Anyway, the critical t for reaching or exceeding significance will be a given point, either on one end of the distribution or on both ends of the distribution. A critical t for alpha is 0.05, marks the point on the distribution where there's only 5% probability of obtaining a t-value as extreme as that, assuming no difference between samples, that the null hypothesis is true. All right, so I've given you some rather complex and abstract mathematical facts and descriptions about this thing called the t-test. I've shown you that if the null hypothesis is true, we would expect the t-value to vary anywhere from 0 to as extreme as -3, +3 for a sample of 25 participants. We wouldn't expect large t-values. We would expect, if the null is true, we would expect t-values close to 0, maybe a little positive or negative, but probably less than 1 if there's really no effect. But if there's really an effect, we might expect that we calculate a t around 1.5 or 2, or if it's a very big difference between effects groups, then we might get a t of 3 or 4 or 5. It just depends on how big the difference is. But if there's really no difference between groups, we're going to find t is equal to around 0. So t is a representation of group difference, how different a group is from another group, or how different a group is from a hypothetical population value. When you are confident that an effect could only be in one direction, like let's say, how much do people like ice cream compared to broccoli? We might expect that on average people like ice cream more than broccoli, and that would be let's call that the positive direction. But if people like broccoli more than ice cream, that could be a negative direction. If you're quite sure that ice cream is going to be more liked than broccoli, we could just test the difference between liking of those two things against the null hypothesis that there's no difference. And we would want to do a one-tailed test for that analysis because we're quite sure that people are going to like ice cream more than broccoli in a sample of 30 people. On average, they're going to like ice cream more. If we're quite certain of that, then we don't need to test whether people also like broccoli more than ice cream, because we're so sure. So we just test one-tailed test, meaning we test whether ice cream is more than broccoli without testing whether ice cream is less than broccoli. So if we're sure about the direction of our finding, we can do a one-tailed test. But if we're only like 90% sure or 95% sure, we should do two-tailed test to catch the possibility, statistically catch for or account for the possibility that our hypothesis was wrong. So you have to really be like 99% sure that your hypothesis is in the right direction before you decide to do a one-tailed test. As you can guess, most of the time we want to do two-tailed tests because most of the time we cannot be so certain about our prediction. Even the direction. We have to be really, really certain about the direction of our effect. like before we even collected data. So before you collect data, you should know whether you're going to be doing a two-tailed test or a one-tailed test. And the one-tailed tests are reserved. They're used rarely, and they're only used when you are almost absolutely certain that you know the direction of your finding, the direction of the effect. All right, so if you guys are going to do a t-test, you're probably going to do a two-tailed t-test. That should be your default. So you can test that hypothesis, the hypothesis that your effect, let me start over. When you are confident that an effect could only be in one direction, for example, exercising group should show reduced body fat, then you can test that hypothesis alone as a one-tailed test. That might even be a bad example, because exercise, it really depends on the kind of exercise. If it's cardio, then we could expect reduced body fat. If it's weightlifting, we might be uncertain. So anyway, right. You avoid testing whether the exercising group gained body fat if you're like virtually certain that they would not. The one-tailed test requires researchers and readers to agree that any effect is almost certainly in one direction, not the other. The benefit of using a certain direction, of being certain about the direction of the effect, is that you can shift one of the two tails of possibility or probability of obtaining a t-value as large as or as extreme as the one that you might find, from both negative and positive ends of the t spectrum so if you know it's not going to be a negative t-value, you can shift the probability of getting a negative t-value over to the positive end of the spectrum, which then increases the probability of obtaining a t that it's almost like a trick. You're saying, I know I'm not going to find a negative t, for example. So I'm not going to find the t-value over here. So I'm going to shift the probability of obtaining a t that extreme on the negative end. I'm going to shift that over to the positive end. And because I'm now testing for at the 5% probability level of finding a t as extreme as that or more extreme, since I'm testing it only in one tail of the distribution, I can increase. I think a better way to describe it is if I go back to this slide. Okay, so look at the red lines. If you look at this red line here, okay, so if we didn't know the direction of the effect, there's only, and we're testing at the probability of 0.05, probability of getting a p-value, probability of a t-value as extreme as that or more. Then we mark the critical t here and here at both ends, because we say there's 2.5% chance of finding a t as extreme as this on the negative, or 2.5% chance on the positive end as well. So the chance of finding a t as extreme as that, we reserve that the t could be negative or positive. But if we say it has to be positive, so we can shift the probability, which is that area under the curve, we can shift that area from one end of the spectrum over to the other end of the spectrum, which then shifts the red line closer to 0, basically allowing us to have a smaller critical t value before we can judge that we found a significant effect. So it's a little bit of a trick. It's a trick that we use when we're certain of the effect direction. I'm quite sure I'm giving you like way too much information, that you don't really need all of this information for your own research projects that you've done, that you're doing now. But I have to tell you this because this is a research methods course, and you have to understand it when you're reading other people's research in published articles. So you have to understand what is the difference between a one-tailed t-test and a two-tailed t-test. And this could be on the test. You know that exercise, okay, so let me finish reading the slide. Say your t-value is 1.8 and the two-tailed critical t is 2.0, but your one-tailed critical t is 1.7. You know that exercise should reduce body fat, and your readers know that too. So you can test for only the possibility that exercise decreased body fat. And if you test only that hypothesis, it means that you can shift the critical t so that you're only testing against the possibility of a t at that level or larger only in the positive side or only in the negative side. In other words, you shift the two-tailed t probability all to be only on one of the tails. All right, that's enough about that. Let's go on to the next topic. Do you guys want a 5-minute break right now?
Yes, please.
Yeah. I don't blame you. I'm gonna start class at 4:24. Okay, take a quick break. All right, it's 4:25. We're gonna start back. Okay, so we're moving on from abstract stuff about one and two-tailed t-tests, going on to something called degrees of freedom. This is again abstract. It's only moderately important, but you have to know it. You deserve to know it because this is because it's part of what it means to be a psychological researcher and to understand our field at the statistical level. We use degrees of freedom rather than sample size when we are calculating p-values, because this slightly adjusts for the underestimating of population variance based on sample variance. Because the population standard deviation is larger than the sample standard deviation. And how do we know this to be true? We know this to be true based on observations. We can observe that sample standard deviations are always or almost always smaller than the population standard deviation. We can show this to be true statistically or mathematically, I think. So anyway, because of this, our field, the field of psychology, has come up with this small correction strategy. Instead of using the actual sample size in our mathematical analysis, when we do things like t-tests and other kinds of tests, instead of using the true sample size, let's say you tested 13 people, instead of using 13 as the sample size, we might use 12 or 11 as the sample size in calculating our statistics. And that small change is our way of adjusting or correcting. It slightly adjusts for the fact that sample sizes usually underestimate population variance. All right, so how to report results of your t-test. Here's an example. So let's say you've done your t-test and your t-test statistics shows 3.07, negative 3.07. So then in your paper, you write, the difference between group A and group B was significant, comma, T. Notice that it's an italicized T. Parenthesis, 9. Now that 9 would be for a independent samples test using 10 participants. So it's really n minus 1. So T parenthesis 9 means T based on 9 degrees of freedom. Such a weird word, degrees of freedom. But DF is what goes inside of the parenthesis, right next to the T value. So italic T, parenthesis, n minus 1, which is for a sample of 10, this would be 9, equals whatever your T value is to 2 decimal places, comma, italicized P for the P value, less than 0.05, or P equals and the actual P value that you calculated to 2 decimal places, usually. The degrees of freedom is in parentheses. The T and P are rounded to 2 decimal places. All right. Any questions? Now, on this slide, I said n minus 1 or n minus 2, depending on the experimental design. Now we go to something called the paired samples t-test. In this kind of test, your degrees of freedom is n minus 2. This is used when instead of 2 groups, you have only 1 group, but you measure the 1 group 2 times. So your 2 groups are really 2 conditions. Condition 1 measured and condition 2 measured. And then you have these 2 columns of data. Different scores are calculated for each participant. And the alternative hypothesis is tested against the null hypothesis that there is no difference between the conditions, that the difference scores should have a mean of 0, because some difference scores will be positive, some negative, and then averaging out to 0. This is, I'm talking now about the paired samples t-test, also called the dependent samples t-test. The reason it's called dependent is that every measurement is dependent on its pair, because every measurement and its other pair, the other measurement, is from a single individual, because every individual is measured twice. Every data point is paired with the other data point from that same participant, because every participant contributes two datums, two data, two measurements. In the case of independent samples t-tests, this is where two groups are tested. They're two different sets of people, and they can be tested in different conditions, or the identity of the group may act as the condition. In other words, we could test like Black people and white people, or old people and young people. And so these are conditions, and they're different groups of people. When the condition is the group of people, it's called a quasi-experimental design, because we're not really assigning people to conditions. People have already assigned themselves to the condition by being old or young, male or female, like that. Called quasi. That's when it's called quasi. Next, we've talked about t-tests. Next, we talk about analysis of variance. I don't think that anyone will be doing analysis of variance in this class, but you will need to use it eventually, like for your senior project, you probably use it. A lot of people will. ANOVA tests are called F tests. I don't know how F came to be the letter to represent ANOVA, but it is. They're used when testing for any difference between 3 or more conditions. So if you have 3 conditions, you have to go with a ANOVA rather than a T, usually. A one-way ANOVA means there's one independent variable. If there's 2 independent variables, it's called two-way ANOVA. 3 IVs, 3-way ANOVA, etc. H sub 0 is that all groups are equal. H1 is that at least one group is not equal to the others. Maybe 2 of them are equal and 1 of them different, then that would be H1. That any of the groups is different from the rest. The F test is calculated. It is the proportion or the ratio of mean squares between groups divided by mean squares within groups. And what are mean squares? Each individual data point is compared to the mean for that group, and that difference is squared. Then you find the mean of all of the squared values of all of the data. That's the mean square. And you can find a mean square between groups and a mean square within groups. The mean square between groups is calculated by, I'm not going to tell you, it's too much information. So this ratio of variance between groups to the variance within groups, well, that's actually it. That's basically it. It's conceptually, it's the ratio of variance between groups to the variance within groups. Larger group variances are indicated by a larger F. So the larger F means there's bigger differences between groups. The F distribution, I showed you the T distribution in an earlier slide. This is the F distribution. That means the distribution of F values that you would be expected to find by chance when we assume the null hypothesis is true. The red line corresponds to the critical F value, beyond which we conclude that there is a significant difference between one or more groups. ANOVA tests. The test only reveals significant or insignificant. It does not tell us which groups differ from which other groups. In order to find out more information about which group is different from which other groups, we need to follow up with post hoc testing. Post hoc means after the fact. Now, if we're gonna do post hoc testing, why wouldn't we just start with that? The reason we don't start with that is because that's like exploratory analysis, and we want to keep our exploratory analyses to a minimum. So already when we do post hoc testing, we're already starting to explore instead of testing an actual hypothesis. The actual hypothesis should be something like, we hypothesize that not all groups are equal. Not all groups are the same. That there's some difference. Some group is different from some other group. So we start with that test. That's the planned analysis. And then we follow up the planned analysis with post hoc testing, which is kind of exploratory, pretty much. So for a within subjects design, we use paired samples t-tests. For a between subjects design, we use independent samples t-tests. Kind of confusing. Why am I talking about t-tests here when we're just talking about ANOVA? I don't know. Maybe a misorganization on my part. Correct for the number of t-tests you run. Oh, I know why. Because post hoc testing is t-tests. When you're doing the post hoc test, you're testing, all right, we know there's a significant difference somewhere, but we don't know where. So we're going to find out with post hoc tests, which means comparing every possible pair of groups. Group 1 versus group 2, group 1 versus 3, 2 versus 3. So that's called post hoc. We can use paired or between, within or between, paired or independent samples, t-tests. We correct for the number of tests that we run. So if we're going to run 3 t-tests, we need to correct for that by reducing our critical t by a factor of 3. So if we do 3 t-tests and the alpha is 0.05, we should compare our observed p-values for each t-test to the hypothetical, to the Bonferroni corrected value, which is the alpha value divided by the number of tests that we run. Sorry that you have to learn these complex words like the Bonferroni corrected value. It's named after Mr. Bonferroni. So if one of your 3 t-tests produced a p-value of 0.02, we would call that not significant, even when the alpha is normally 0.05, because there's a higher likelihood of a type 1 error. So we have to be more careful and cautious when we do these post hoc tests. Because they're kind of exploratory, we want to minimize the critical p-value. We have to shrink it. This slide is to remind you to be careful about type 1 errors and type 2 errors. And it illustrates both of them with this picture. So the picture on the left is a man who's not pregnant. Picture on the right is a pregnant woman. And we can make decisions to reject the null hypothesis or retain the null hypothesis. When the null is false and we reject it, that's a correct decision. When the null is false and we retain it, meaning that there's a real difference, but we could not reject the null because we just didn't find it. We just, our data didn't support. So we could not reject the null, then that means we say, well, we didn't find an effect, but really there is an effect in the population and we didn't know about. That's called a type 2 error, the failure to reject the null hypothesis when we ought to have rejected it. Then there's, what about when the null hypothesis is true, but by chance, our data suggests there's a difference? Then that is a type 1 error. That's the one we need to be particularly careful about. And then when the null hypothesis is true and we retain the null hypothesis, we say we do not reject it, then that is a correct decision. All right. Small p prejudice and p hacking. This is a kind of professional issue that is very important for psychology students to know about and understand. It wasn't always taught about historically, but now it's becoming more and more threatening to our field and more important for us to understand. Small p prejudice and p hacking. Most journals, even now, are prejudiced against non-significant results. If you find a non-significant result, most journals are hesitant or basically don't want your paper. But this is starting to change slowly, but it's gaining momentum. Journal readers want to read significant findings, and journals cater to that. So if you find a non-significant effect or result, you might not be able to publish it. That doesn't mean that your research is worthless. It just means that the journals think it's worthless. Really, it's not worthless. It's important. We really ought to be publishing null results also, but we got to work with what we have. This publication prejudice has inflated the type 1 error rate and exaggerated the effect sizes of published findings because only bigger significant effects end up being published. So we're already filtering the population of studies that have been done. We're only filtering and publishing only the ones that find the biggest effects, even if those effects were big based on chance. So this is a selection effect. Only these results pass the publication filter from the population of studies done, and insignificant effects are put in a file drawer. This is called the file drawer problem. Whenever people don't literally put their work in a file drawer anymore, it's all on computer. But back in the day, researchers had their, everything on paper, and they would, if their results came out unfortunately not significant, then they would say, oh, damn, I don't want to throw it away. I've done all this work, so I'm just going to stick it in my file drawer. Worse, insignificant findings can be made significant by removing outliers or data that would reduce effect size without honest, justifiable reasons. This is ethically unsound, ethically poor. Performing many tests without correcting for inflated type 1 error rate. So if you do many tests, like kind of exploratory analyses, and you don't correct your critical p-value based on the Bonferroni correction or some other kind of correction, if you don't do a correction for the number of tests that you've done, that is also a way to make your results appear significant when in fact, because you didn't follow the professional protocol of doing that Bonferroni correction, you're making your results look like they're significant when really you should have decided they're not significant. So that happens a lot sometimes, but we should try to not do that. Testing multiple times after adding and removing participants That's also another way of p-hacking. And there are other ways of p-hacking. So for the sake of science, I ask you not to do that, please. I know that it's hard to make yourself follow these professional ethics sometimes, because sometimes, you know, you'll have done all this research and spent all this time, and then if you can publish it, it's really good for your career. Maybe it helps you get a job. And if you can't publish it, then maybe you can't get a job, or you can't hold on to your job. So this comes with such major personal life implications that it's really hard to make a professional ethical decision about how to report your results. So this is a really critical problem in our field, but there's good news. We are starting to correct our field because we recognize this as a problem. We've been recognizing it as a problem for decades, but we haven't done anything to fix the problem until only the most recent decade. In fact, only the most recent 5 years or something. It's really starting now. It's really picking up momentum now that we are correcting for these kinds of problems. We're correcting the field by working at the level of correcting journals and becoming more aware of these problems. A recent solution to p-hacking. So now I'm going to talk about this, the latest positive things in our field. Taking this problem seriously, a quickly growing number of journals are encouraging registered reports. You're going to start hearing about these more and more as the years go by. This is going to become the new standard, the new professional standard for our field. Researchers can submit their papers for peer review before collecting data. This is our solution to the p-hacking problem, is that we can submit for peer review before collecting data, so we don't even have to worry about whether the results are going to come back as significant or not. This is also encouraging the publication of results that are not significant. So even though it's not significant, we should now be able to read about non-significant findings in the research literature now because of this registered reports phenomenon. Reviewers will read, critique, and either accept or reject the paper before the data are collected. Once accepted, it is registered and it will be published regardless of the results. This is huge. This is a big game changer for the field of psychological science. This makes our field much more scientific. So this is a very big positive thumbs up for psychology as a field, as a professional, as a science. This is a big thumbs up. This demonstrates journals' commitment to scientific values, addressing research questions that are actually important to researchers of this topic area. Because researchers want to know, is there an insignificant effect? We want to know that. We want to know that someone's found an insignificant effect. That helps us decide what to test further, how to extend the research further. So this also demonstrates methodological rigor, strong, good research practices, ethical research practices, not just statistically significant findings. If a positive decision on research proposal is made, data collection commences, analyses are performed, the remainder of the paper is written, which means the results section and the discussion section. Because the registered report is registered by writing the intro and the method. So we leave unwritten the results and discussion until after collecting data. But yeah. All right, and then the paper is accepted regardless of significance. That's a huge thing. All right, looks like 8 minutes left of class because I'm trying to end at 5 o'clock. Statistical power is defined as the ability to reject the null hypothesis, assuming that it is false. Usually with null hypothesis testing, we assume the null is true, but power is the ability to reject the null hypothesis. Traditionally, we want power to be at or above 0.80, which means we should be able to detect an effect. If there is a real effect, we should be able to detect it 80% of the time. That means that our power is at 0.80. To get power at or above 0.80, we have to increase our sample size or increase the manipulation quality. This means that based on chance, if our power is 80%, then 20% of the time we fail to identify an effect. That's called the type 2 error rate. So when power is 80%, the type 2 error rate is 20%. When power is 70%, type 2 error rate is 30%. They are always balancing. I mean, they always add to 100%. If you reduce the type 1 error rate, say let's say you say, all right, I want to be super sure of the results that they're not type 1 error rate. So I'm going to reduce my alpha level to 0.01 instead of to 0.05. So I'm going to go more conservative. If you do that, by reducing your type 1 error rate, you concomitantly, meaning simultaneously, increase the type 2 error rate and vice versa. So you can reduce type 1 errors, but you also increase type 2 errors when you do that. So it is a balancing act, and the traditional balancing that we try for is 5% chance of type 1 error and 20% chance of type 2 error. That might sound pretty high, the chance of type 2 error, but we think that type 2 error is less damaging to our field, less risky to find. So we think that the type 2 error is not as bad as the type 1 error. That's why we want the type 1 error lower than the type 2 error. You can increase the power by increasing the signal to noise ratio. I said earlier that we can increase power by increasing sample size. Yes, we can increase the signal to noise ratio by increasing the signal, which we can do by increasing the sample size and manipulating conditions more strongly to increase the expected effect size. Or we can reduce the noise by testing within subjects instead of between subjects and increasing measurement precision. And I think we could say that the bigger sample size also reduces the noise. So basically all of these strategies, these 3 strategies or four strategies, increase the signal to noise ratio. By increasing signal to noise ratio, you increase power, statistical power, which means you reduce the type 2 error rate. Plus, you also reduce the type 1 error rate. So when you have a really good, strong signal to noise ratio, you're reducing the type 1 and type 2 error rates smaller. But otherwise, our tradition is to allow 5% type 1 20% type 2. If you add it up together, there's a 25% chance. That sounds really high, right? 25% chance of making an incorrect conclusion based on looking at your p-value, based on doing your null hypothesis test. And I know that sounds really high. I don't know, we're not used to thinking about it as being that high, but yeah, that's what we work with. Calculating power. There are online calculators to calculate how many participants you need. You can download a power calculator from this website or this one, and I have linked to those words. I would like you to retrospectively calculate your study's observed power using a power calculator. You will need your observed standard deviation, your sample size, your observed effect size, and you can estimate the population standard deviation, which is called sigma. At the population level, it's called sigma. At the sample level, it's called SD, from your observed standard deviation and the expected effect size based on your observed effect size. Report this power estimate at the end of your results section as the following words. You can quote these words exactly, or you can paraphrase if you like. A power analysis was conducted retrospectively. The observed power was, and then cite your power. It'll be like 0 point something, meaning that there was, and then you can use the same number again, likelihood that an effect of this size would have been detected if one really exists. Feel free to use the exact words. All right, this is a practice exercise. You can do this on your own. This is more practice. This is practice to conduct a one sample t-test. You can do that using online t-test calculators. Sorry, I meant to give you more time and to do this as a class, but we're running out of time. And then here's another exercise. Calculate inferential statistics without SPSS or Excel, just using Google Sheets, or you can use Excel because Excel does this also. You can use this to calculate R values, t-tests, p-values. So you can do all of the necessary statistics for your research study to write your results section using free online calculators and free calculators with Excel. For help and consultation, if you have any uncertainty or need more guidance to analyze your data, please email me. Here is a research paper checklist I made. Please use it to make sure you didn't skip any important components of your paper. And I will be grading your paper using a similar checklist. Needed in your final report is descriptive and inferential statistics. I expect these in your report. I also expect you to make a figure. Next week is your final exam. It's multiple choice, open book, open internet, open collaboration. The exam will be Tuesday, May 4 from 1 to 3 p.m. As with the midterm, I allow you to work independently or with others. In 2 weeks, your paper is due. 1 submission per group, please. In 3 weeks, each group will present a 5-slide presentation of your research. Be prepared to present your study to the class through Zoom and submit it on Blackboard. And of course, submit your paper on Blackboard as well. All right, that's the end of the lecture, and the time is 5:01. I don't feel very comfortable about skipping all of those exercises that I just skipped. Someone wrote here, the May 4 is Coronation Day. Can someone else verify that? Is that true? Can someone please verify that? Because I don't know. This is a surprise. Someone else thinks it's a holiday. Can we get a third person to verify this? I'm surprised because I thought I knew all of the holidays already, and I thought that, I mean, I crafted my syllabus with that in mind. Someone asks if coronation is on May 5. Huh. Someone says it's, I don't know what CUNEX is, but probably Chula website. Check that May 4 is this year, not last year. I'm gonna look this up also. It's an app for Chula. It's May 4. Huh. Okay. Well then, because May 4 is Coronation Day, we need to postpone everything by a week. So that means your final exam is not next week, but in 2 weeks. Okay? So we are doing final exam in 2 weeks, paper due in 3 weeks, presentation in 4 weeks. I guess that's what we're doing. We're pushing everything by 1 week. Is that okay?
So instead of the paper being due on May 11th, it'll be due on May 18th
Yeah.
later? Okay.
Yeah. Okay. So I will fix our syllabus, and that's that. So not everyone has come to class today, and right now there's only 24 participants in the class. So feel free to pass on the word. I think I will send a message on the line group about this, that everything is delayed by 1 week. All right. As I said, I don't feel really comfortable skipping over the class exercises that I just skipped over. I'll show you on the slide. So we've got all these practice exercises that I really would like to do with you as a class. So I think I'm going to hold off for now. And I think next week on Coronation Day, I will have an optional short class to go over these exercises as a class. And then in 2 weeks, we'll have our final exam like we talked about. Okay, someone said, for presentation 1, can each group record the video and send you the link instead? Oh, interesting. I mean, if you want to do that, yeah. Oh, maybe you have to do that because that would be useful. I mean, that would be helpful because of the screen sharing option. I think I'll leave it optional for now. Well, what do you think? Can you give me some feedback about this? I see that you did it for Ajahn Guk's class. Oh, I see your point. C said that our schedules would be more flexible. Like if some students can't make it to class, but they have already submitted by email their presentation, then I could still give full credit to all of the participants. That makes sense. It's hard to give credit to someone who didn't participate. So that is a strong point. I like it. I like that idea. Can we do that? Can I have you guys recording would be great, someone says. Okay, let's do it. Someone else, I support, I'm okay, I think it's better. Okay, great. I feel like there's consensus. So we'll do the 5-slide presentation as recording. And you send me your recording and I will play it for the class. Thank you. That sounds great to me too. Excellent. Okay. That's our plan then. Thank you. Thank you guys for that great suggestion. Email, yeah. Please email it to me. Excellent. Thank you guys for staying the whole 4 hours. We lost some participants along the way. I understand it's 4 hours is a long class. Okay, so optional class next week to go over the practice exercises. I think that it would be helpful for you, educational. So if you can, show up to Zoom. If not, it's totally okay. But if you don't come to class next week, then try to do the exercises by yourself if you can. And if you can do it, then you don't need to come. Yeah.
For the presentation video, so will we still have a like presentation class, or does everyone just have to send it to you through a video?
Oh, great question. I would love to skip that class if everyone can send their presentation. I could combine that class with the previous week class where people are the April 18 when your papers are due. I could have your papers due and then present your videos to the class.
Okay.
That would be awesome. Let's do that. I will announce that on the line group as well. Someone asked me, and thanks for staying a little longer past 5 o'clock. Someone asked, is this optional? No, it is not. You get graded for your presentation. This is part of your grade. Does everyone have to send through video? 1 per group. And yes, video, please. It can be video or audio. I'll leave it up to you, video or audio. But everyone in your group should speak. Do we have to show our faces in the video? No, it can be audio only. What is the due date of the video? That should be April 18, the day that it's due, the day that I show it, it's due. And if you didn't send it to me, then you better have it ready to present in class that day. All right. Yeah. Thanks for all these great questions. You're really helping me to put it all together. Any other questions? If not, thank you. And great class, great double class, making up for last week. And have a good coronation day next week. Maybe see you, maybe not. See you in 2 weeks for sure for the final exam. Have a good day. Goodbye, everyone. Bye.